We were looking at logistic regression and on Monday, but I thought I'll just take a step back. I saw a lot of comments on Piazza about the discriminant analysis. So I'll quickly give a brief primer to that, but if you have any questions, please interrupt me. So the idea is that I'll just go through the basics of Gaussian discriminant analysis, which will help you do the first problem in assignment 2. And of course, it will help you in other things as well. But feel free to, if you have more questions, just interrupt me at that point and ask me. Then there were some questions about regression, which I don't remember right now. So if you do have questions, please ask them today, and I can clarify them as well, because your assignment is due next week. All right, so Gaussian discriminant analysis, right? So the idea there is that so later on we'll be talking about discriminative classifiers, so don't get confused. Those are two different things, right? So this is sort of like I'm stepping back, discriminant analysis, right? So this is an extension of naive-Bayes classification, right? So you remember naive-Bayes classifier. You did a couple of problems in assignment in midterm as well about, you know, all that smoking thing and the tennis playing. So there the idea was that you're trying to predict the probability of your target, which is y, right? And y can take 2 values or 3 values, can take discrete number of values, given some x, right? So you were supposed to compute what is the probability of y to be something, right? So to be malignant, given x, right? And in the naive-Bayes classification, we made a little simplification, which is that we assume that this x, right? These are your input attributes. So we assume that this x is actually a vector, right? A vector with d elements in it, and each element is itself discrete, which means each element. So each of your feature, right? So we call each one of them is a feature, and for naive-Bayes, right? For naive-Bayes classification, we assume that each feature, so let's call these x1, x2, and so on. So of course this is probabilistic classification, right? So we assume that each one of these is also a random variable, right? But we assume that each one of them is a categorical random variable, which means that it can belong to one of few categories, right? So we assume each xi is discrete. Discrete means it can take a few values, right? And then we assumed that each one of them is also independent to each other, and then that helped us simplify the equation. So that is, I hope you all remember that part, right? But then we made an extension. We said, okay, what if these values are not discrete, right? What if they all range from -infinity to infinity, which makes it a little more practical, right? Because a lot of the features that you measure are like that, right? They could be something like a weight variable or height or size, something like that. So then we make an extension. What if each xi belongs to R, right? So it belongs to the real number line, right? So then we move to, then we saw that similar concept can be applied there as well, except that your probabilities would change, right? So we can say that we can still have a naive-Bayes classifier, right, NBC, where the probability of y equal to malignant given x, right, becomes probability. Now we first apply the Bayes rule, which says that what is the prior probability of y equal to malignant, of course, right, times the conditional probability. What is the probability of x given this is y, right? This is the same as Bayes rule as well. And then we said that, okay, this is of course one quantity that we can compute by just looking at how many labels are there in the training data of each class, right? But this part, this we simplify. We say this is a product I equal to 1 to d. What is the probability of each xi, each one of these components, given y is malignant, right? Actually, this is still naive-based classifier, because so far we have not really talked about what is the form of this probability, right? And this is where the split happens. So if we are talking about classic naive-based classifier, we say that this is nothing but we assume that xi is a categorical random variable, which means that you can model it as a as a Bernoulli distribution or as a multinodal distribution, depending on how many categories, how many values it can take, right? But for Gaussian, when xi is normal, when xi is real, right? When xi belongs to R, then of course you cannot model it as a Bernoulli distribution. Then we assume that xi is actually a normal distribution, right? Normal means a Gaussian distribution, which means that it will have some mean mu I and some variance, right? We remember what a normal distribution looks like, right? Which means that now this quantity can be written as py equal to malignant times, and then this is a product over all d, and whatever the PDF of a normal distribution is. And the PDF of a normal distribution has a very beautiful form. It is under root 2 pi sigma I, right, times exponent minus half whatever xi value is minus mu I square and a sigma I square, right? That's easy. Now, because this has such a beautiful form, which means that you can actually write it as this, py equal to malignant. This would look like, if you actually multiply all of these d quantities, right? So you will see that all of them have a 2 pi, under root 2 pi. So this actually becomes 2 pi raised to power d, because you'll multiply those. And then you would be multiplying all of these sigma 1, sigma 2, sigma 3, and so on. This would actually look like 1 by 2 times exp minus xi, so x. And I'll talk about the form of these things. So there is no magic here. All we do is we actually open this product and multiply them all together. This would start looking like this, where sigma is nothing but a matrix, a diagonal matrix, in which you have sigma 1 square, sigma 2 square, until sigma d square, and zeros here. And mu is nothing but a vector with mu 1, mu 2, mu d, and x is of course all your inputs in a vector, right? This is just by multiplying this together, right? Which means that suddenly if you look at this expression, right, it looks like a multivariate Gaussian, right? This is a PDF for a multivariate Gaussian in which mu is the mean and this capital uppercase sigma is your covariance matrix, which means that you can write this as py equal to malignant times the PDF of a multivariate Gaussian with mean mu and this as sigma. All right. So, so this is the idea, right? So now, even though we made this simplification over here, we assume that all of our x's are independent of each other, and then we said each xi by itself is a normally distributed univariate random variable. But when we did the math, when we added it all up, it got to this form, right? Which essentially means what you're assuming is that your x, the whole x, right, is a random variable distributed as a Gaussian, as a multivariate Gaussian. All right, any questions so far? So now how do we use this, right? So that is what I ask you in the assignment is, so what we are saying is that for each value of y, so remember y can take few values, right? So let's say y belongs to a set of malignant and benign, which means that it can only take two values, right? So for each value of y, we need to compute these. We need to compute estimate or learn or compute mu 1. So let's say y is, we call this 1 and 2, right? So mu1 and sigma 1, and estimate mu2 and sigma 2. So if you're given some training data, right? So remember, a training data set in this case are bunch of x's, right? And then their corresponding labels. So these could only be ones or two. So let's say I arrange them such that all the top few are ones and last few are twos, right? So you can look at this part of the data. So this is all your x's for the first class, all your x's for the second class, right? So you can estimate, assuming that each x here is coming from a multivariate Gaussian. I have shown in the past how to come up with estimates for mu and sigma, right? That we do typically using MLE, and we can get more fancy and put a prior on that. But right now we're assuming that we can do an MLE estimate. So you can do MLE and get these two estimates, right? So that tells you what is the probability, what are the parameters of each one of these class conditional distributions, right? So once you get that, then you can simply apply this, right? Then probability of y equal to 1 given some x essentially becomes, or it is probability of y equal to 1 times probability of x given y equal to 1 divided by this whole constant term denominator, which will just be a constant term. So I'll call it z, because at the end you just need to compare, right? So you'll compare y equal to 2 given x. So z will be the same for both cases, so you don't really have to compute it, right? So this is essentially the idea behind discriminant analysis. So in the training phase, you estimate these values. In the testing phase, when you are given a new data point, you compute these things, right? Now, in the assignment, what I say is that now, how do you compute? This we have seen, right? If you want to compute these prior probabilities on the class, essentially you just say, okay, what fraction of your training data is 1, right? It tells you, if I don't know anything about x's, then what is the prior probability of y? So that you can do just by looking at the labels, right? But in the training data that I have given you, all of these are fairly similarly distributed. That means all of these values will be close to equal. I mean, they will be equal to each other, which means that they won't really have much effect on the output. So you can just compute this, that should be good enough. Okay, so if we ignore the prior for y, which is py equal to 1 and py equal to 2, then all we need is px y equal to 1 and px y equal to 2, and then whichever is higher, you say that is the class, right? That is the predicted class. So that is the idea behind discriminant analysis, all right? So then we talked about two different versions of discriminant analysis. In one, we assume that we just go this way. We compute mu1 and sigma 1, mu1, mu2 and sigma 2, and use it to compute these values, right? And in another one, so that is called a quadratic discriminant analysis, which means sigma 1 is not equal to sigma 2. But in another one, we force both of these sigmas to be the same, which means that maybe you pool all the data up and compute the pooled MLE. Pooled means just put it all together, right? Then, so we force sigma 1 equal to sigma 2. Of course, mu 1 and mu 2 are different. They're different in both cases. Then the resulting classifier that we get is called LDA, or linear discriminant analysis. So when you implement this, you will see the reason why we call it quadratic and linear. All right? So another interesting thing that I talked about long time back was that you can also think of this, because this value, right, is nothing but the Mahalanobis distance between x and mu. So if x is a data point and mu is another data point, right? So if you want to compute Euclidean distance, this is a sidebar discussion. So Euclidean distance, I'm assuming all of you are familiar. In vector notation, we say Euclidean distance between two data points is like this. right? Which is kind of like x1 minus mu1 square plus x2 minus mu2 square, right? And so a square root of this, but let's ignore the square root. So this is the Euclidean distance, and then, but the Mahalanobis distance is written as this. So you are also weighting it by this covariance. And if you refer back to the notes, we do talk about why we do that. But you can think of this quantity as basically you're trying to compute the Mahalanobis distance of your data point to the mean, right? So if we assume that sigma is the same for both classes, right, then essentially what you are doing is when you compute these values here, these two values, right, assuming for LDA case, what happens is that all you're doing is you're computing the Mahalanobis distance of your new data point to both means, and whichever is closer, you say that is the class, right? So that kind of follows a normal intuition, right? So if I give you two classes, if I give you a bunch of data points in this 3D space, I say that class 1 all points are over here and class 2 all points are over here, and then I say here's a new point, which class does it belong to? You will essentially try to see, okay, which one is it closer to, right? So that is the idea behind discriminant analysis. Of course, when these sigmas are not the same, right? In the case of QDA, then we are not just computing the Mahalanobis distance, we are also multiplying it with this. So this would also have an effect. But for LDA, it is just pure Mahalanobis distance. Any questions so far? Two questions. I'll just start here. What do you mean one? Like a formula? Yeah. So at the end of it, if you remember, the way we compute the MLE is we try to compute the total probability, the likelihood of the data set, and then we maximize it, right? So at the end, when you maximize it, you will get one expression for mean and one expression for covariance.
So is that true across all different, like,
We would like it to be. See, at the end of it, all we do is we try to maximize our likelihood, right? So when we maximize our likelihood with respect to your parameters, if the function is well formed, we should be able to get a closed form expression for your estimate. So in many cases that we talk about, it ends up being one expression. But if your likelihood is more complicated than that, then maybe you won't get a closed form expression. Then you have to do some other things that we won't talk about. But in this scenario, it's just one formula that you get at the end. Yeah.
Yes, I just have a couple of questions about some of the basic probability stuff that we're using. So if x is a continuous variable, why is p of x not 0? The probability of a single point?
That's an excellent question. So that goes back to our initial discussions, right? So the point is that if x can take infinite values, then it's actually not right to write p of x to be something, because everything will be close to 0 because it needs to sum up to 1. But here we actually, when I write p, I should be writing small p. It's actually the PDF of x at that value. So remember the notion of a probability distribution for continuous variables, right? We don't have a p actually, because all the p's will be close to 0 because they need to sum up to 1, right? So what we have is, instead of that, we have a small p of x, which means what is the density of this random variable at any x equal to x, and that gives us some function like this. So this should integrate to 1. But these values, so we are being a little lazy here and interchanging that notation here. But whenever we talk about continuous distributions, we do refer to PDF rather than the actual probability. Any other questions? Yes. Well, at the end of it, you would see this, right? This will be a probability because y can only take two values, right? So when we compute these two quantities, because of this normalization factor, these will sum up to 1, right? So these are probabilities. But when we are computing these two things, then these are not probabilities. They are actually densities because x is can take infinite values. Yeah.
Where does the Z come from?
Oh, so this comes from Bayes' rule. So this is just because I was being lazy. But this, we should be writing it like this. Py equal to 1.
Oh, the summation of
Yes, plus py equal to 2. Right? So what happens is, because this would be the same in both cases, and since all we are doing is comparing, we don't really compute it. Any other questions? Yes.
The second part would be P equal to X divided by Y equal to 1 and Y equal to 2. Do we calculate that by MLE? What was it?
And so this part,
Yeah. The second part.
this one. So this is essentially this, right? So what we are assuming is that X is a multivariate Gaussian given this class. So we have the MLE estimates for the mean and variance. So all you do is you compute this by using this formula, but the mu and sigma is for that class, right? Any other questions? All right. So that is sort of my quick introduction to, a recap of discriminant analysis. And that's what you have to do for the first question. Then are there any questions about assignment in general? Linear regression part? Yes.
In LDA, we know that the sigma 1 is equal to sigma 2, but what about the mu part?
Mu has to be different. Yeah, because if you set, if mu is also set to be same, then you'll always get the same value, right? Because what you would compute are, see, for a new data point, you will compute this. For malignant, mu1 and here sigma 1. For benign, you will have mu2 and sigma 2. In the case of LDA, that will be same, but mu has to be different. So you will compute the mu using MLE for these individual sets, but the sigma will be computed using the pooled set. Any other questions? Yes.
So to find the sigma of the LDA, we have to compute both of them, and then we will have mean.
No. What I'm saying is to compute the, well, you could do that as well, but the traditionally what we do is we do something called pooling. We just put all of them together. We forget about the y, and then we compute the sigma using MLE. So that will give you one sigma for the entire data set. What you said earlier was you compute sigma 1, sigma 2, and then take an average of that, right? It might work, I don't know, but typically we do this pooling business. All right, so let's move on. There are no other questions. So last call for any questions about the regression part. If you don't, then yes. The question from okay. This was 7? The first one? All right. So let's look at this quickly. So this is problem about linear regression. You have a very simple data set in which you have this as your x and this as your y, right? So essentially what you had to do was, and then there were 3 scenarios in which you were just doing simple linear regression. So I gave you 3 possible weights, right? And the 4th one was slightly different. In this one, we were doing a little bit of polynomial expansion of your original data and then applying these weights, right? So in this question, we were not really learning anything. I was already giving you some weights, right? And then you had to compute which one gives you the best likelihood of the data, right? So the likelihood, if you remember, in the case of linear regression, this is your y's, right? In linear regression, we assume that each y is a normal distribution centered at W transpose X, right? So what we do is we compute, so what will be the likelihood of this data point? Because we assume each data point is a normally distributed random variable, right? So which means, so let me go here. So right now we are looking at gradients 7, problem 1. Right? So let's say this is your data. So your x and y. The first data point was 11, x is 11 and y is 6. Okay? And then your w, one of the w's, is 0.30, 0.50, right? Which means this is the bias part, I think. I said the first one is the bias, right? First component is bias and this is w1, right? So and then you have the entire data set. So how to compute the likelihood of this data set is you first compute the probability of every data point and then you essentially multiply them up, right? So, and we also assume that sigma square in this case is 0.01, right? Because that's given in this thing. So because in linear regression we assume that y is a normally distributed random variable centered at w transpose x, comma sigma square as the variance, right? Which means that for this y we say what is the PDF of y? What is the p of y equal to 6? It will be 1 over 2 pi sigma square, right? Under root 2 pi sigma square exp y, which is 6, minus w transpose x. Now, what will be w transpose x? Because this is this, right? And x will be, so w transpose x will be 0.30, 0.50 times 1. I add the bias term and 11, right? So it will give me something, right? So that will be my value. I don't know what it will be. 0.3 plus 5.5, 5.8, right? So this will be W transpose X. So all you do here is I just 6.58 square minus 1 over 2 sigma square. So sigma square is 0.01, right? So this will be, so then you'll have to compute this. This is easy to calculate. It's just numbers here, right? So now this is the probability density at each data point, and now you can compute it for every data point and then multiply it. So that will be the likelihood of your data set. Yeah, because you're going to compute the likelihood of this entire data set given these weights, right? So yes, so because eventually you have to compare, right? So what you will then do is you will repeat the same process for these as the weights, and then these as the weights, and then these as the weights. But in this case, of course, you will expand your data set to make it x and x squared. So for this case, what you will do is you will replace 11 by 11, comma 121, 18, comma 324, and so on, right? So that is the idea, and then you compare. But that is if you are just computing your likelihood. But in some cases, I also want to know if we put a prior on your weights. So this is what we did a couple of classes back. So if we compute a prior on the weights, then we have to also multiply it with prior. So you compute the likelihood, which you have done, then you multiply it with the prior on the weights, and that gives you the posterior, and then you use that to compare. So that is the idea. Any questions about that? Yes. The handwritten thing?
Yes.
Right. So in some sense, if you think about how we compute the best weight, right? Here what we did was we were given 4 or 5 weights or 3 weights, right? You compute the log likelihood and then you find the one with the highest value. So that is a manual way of finding the best weight. But in reality, you will have infinite possible weights. So then you will have to do this compute the likelihood for each possibility and then find the best one, right? So of course you can't do it manually. There are infinite possibilities. So you use some optimization and get the expression, right? Yes.
In this case, how would you compute the prior? Would it still be from the Y data set?
No. So you see, you have to be a little careful when you're reading the question, right? So we are putting a prior on weights. So in Bayesian regression, right, we say that our W is also a Gaussian, is also a random variable, right? Which means that there is some P of W that is available to you. Now, in this case, what I've assumed that this W is actually a normally distributed random variable with zero mean. Zero, I make it bold because W is for the first three cases, it's a two-dimensional vector, right? So this will be actually two values of zero. And then there will be a sigma, which will have four entries because it's a 2D random variable. And in this case, I assume that it is 0.01 at every. So it's 0.01, 0, 0, 0.01. Right? So the P of W, now what is this? As I just mentioned earlier, right? You can write it as 1 over, again, the same business, d by 2, determinant of sigma, exp minus half, whatever, W minus this mu, transpose sigma inverse W minus mu. Right? So this will be the prior, because you're assuming that your weight vector has some prior probability, and then you use this and you multiply it with whatever total likelihood that you get by computing this, and that gives you the posterior, and then you use the one that has the highest posterior. Any questions for that? Yes.
On the last, the calculus before for P, Y, delta X.
Right.
On the denominator, it was square root of 2P sigma squared.
Right.
But on the previous calculus, in the denominator, the last slide, the last page, you put square root 2P sigma without the square.
Sorry, it is sigma. I'm sorry. Yeah.
And the other one, the denominator of between the brackets is square, right?
That's always square. Right.
Okay.
Yeah, sometimes I make mistakes with these expressions, but these are, you should always refer to the standard expressions for Gaussian distribution. Any questions so far? All right, great. Okay, so so that concludes our discussion on this. Hopefully this will help you in your assignment as well. And now let's move on to the main topic. Which is logistic regression, right? So we were looking at it last time. And the way we started was this discussion about how logistic regression is different from some of the other classifiers like LDA or QDA or naive-based classification. The difference is that it is what we call a discriminative classifier and not a generative classifier, and we have talked about it. But the main thing you want to remember is that in logistic regression or in any discriminative classifier, we directly model y given x. Directly the posterior for y. We do not model x given y and then compute y given x. Directly model y given x. And the reason why that helps is because it makes it reduces the complexity of your algorithm. And that's not part of the scope. That's not within the scope of this course. But there is a whole discussion on how this is related to the VC dimension of the hypothesis space. And then the idea is that discriminative classifiers, they can actually learn faster. They can learn with less data than generative classifiers. So that's their benefit. But this is something different. All right. So then comes what is logistic regression, and then we said that in logistic regression. So you can think of logistic regression very similar to linear regression, and you can see the term regression here, even though it is a classifier, right? We still use logistic regression as its name because that's how close it is to linear regression. So in linear regression, we assume that y is a normally distributed random variable centered at W transpose x. So it's a normal distribution. In logistic regression, we assume that y is a Bernoulli distribution, okay? With parameter, now Bernoulli is your coin tossing, so of course it has a one parameter which is theta, and theta is computed as sigmoid of W transpose x. The reason we use sigmoid is because that kind of squashes your W transpose x to be between 0 and 1. Because remember, when we are doing coin tossing, your theta needs to be between 0 and 1 because it's a probability, right? So that's easy to understand. The other thing is that logistic regression learns a linear boundary, which means it's a linear classifier. So I'll give you a quick example using sklearn. So what I do here is I create some data set, all right? So let's say this is my data set. It has two classes. It has two dimensions or two variables, x1 and x2. So there are some red points and some blue points. Then using implementation of logistic regression from sklearn, right? I train a classifier like this, and then I fit it to the data that I have, and then I use it to predict, all right, and then try to plot the boundaries. Now this is kind of like what you're doing for QDA and LDA. So I've explained that earlier, but this is the boundary that you get, all right? So all the points that are on the left side of this line are are assigned class blue, and all the ones that are on this side are assigned class the next one, the red, right? So what you see is that even though the data here was not really, what should I say, suited for a linear classification, right? But because of its inherent nature, logistic regression will always draw a line, all right? But then we have seen before that you can always do the polynomial expansion or some other, polynomial expansion or some other kind of expansion and get a non-linear line. But by itself, logistic regression is always linear, all right? So that's the idea. So the way we use it is that once we know the weight, W, right, a new point comes in X or X star, we quickly compute sigmoid of W transpose X star, then toss a coin with that probability. If you get heads, then it's positive, otherwise it's negative, right? But the interesting part in the logistic regression is how you learn these parameters. How do you learn W given some training data, right? So we'll look at it now. All right, so the training. So one way to do it, of course, is MLE, right? So what we assume, so first we assume that Y, your target, has two possibilities. So it's a binary classification, and let's say it takes two values, 0 and 1, all right? So then we want to compute what is the likelihood of the sample. So let's say you have one training data point, Y, and if it is 1, then probability of Y to be 1 will be theta I, right? Because we are assuming that yi is a Bernoulli random variable, which means that probability of heads is always theta I. And as we have seen in the past, theta I is nothing but the sigmoid of W transpose xi, which can be written as this, right? Which means that if yi is 0, then the probability of yi will be 1 minus theta I, which is this, which is 1 minus of this thing. Maybe it works out to this, I don't know. But anyway, it's 1 minus theta I. Which means that in general, if I can write that expression as this, P of yi is equal to theta I raised to yi, 1 minus theta I, 1 minus yi. So what will happen is that if yi is 1, then this part, it will be theta I raised to yi, or theta I, right? Yi is 1. This part will go away because 1 minus yi will be 0. And if yi is 0, then this part will go away and it will be this. So it's basically a nice way to write the same thing. Which means that now you can compute the log likelihood of your entire data set, and it will look like this. So I'm going to quickly write it step by step. So for one data point, so for one training data point, right? Let's say it is yi, xi, and yi. So this is my training data point, the data and the label, right? So what is the probability of yi? It will be equal to theta I raised to yi 1 minus theta I raised to 1 minus y. Or this we can also write probability of y equal to yi, right? Where theta I is 1 over 1 plus e power exp minus w transpose xi, right? So this is easy to see why this is so. which means that likelihood of my entire data set, likelihood of D, where D is basically a set of these xi's, yi's, right? I equal to 1 through n. So if you have n data points, then the likelihood L of D is just the product of all of these, right? So it is product I equal to 1 through n, theta I, yi, 1 minus theta I, 1 minus yi, right? Uh, and the log likelihood, because this is a product, we don't like product that much, so we will convert it into log likelihood, and that becomes log of, or summation, becomes summation I equal to 1 through n, log of theta I yi, 1 minus theta I, 1 minus yi. And you can open this with the log to n, it becomes yi, because y will go here, log theta I, plus 1 minus yi log 1 minus theta I, right? Where theta I is always this. So theta I can be computed using w and xi, right? So if I want to be a little more particular, I will do that. So I will say it is 1 over 1 plus exp right? So using your training data, you can compute the log likelihood like this. So now if I want to find the W that is optimal, I just try to maximize it, right? So that's our standard procedure. We can maximize LL of D for W. So the W that maximizes that is the MLE estimate for your logistic regression, right? That's standard methodology. We did something similar for linear regression. We've done the same thing for other classifiers as well, perceptrons, neural networks, everywhere, right? We had some expression for either error or log likelihood, and we are trying to maximize it. However, in the case of logistic regression, what happens is that there is no closed form solution for this formula, which means that if I compute the derivative of this with respect to W, right, that we can do. But when you try to set it to 0 and find the best W like we did in linear regression, that won't happen just because of the form of this, right? So which means that you cannot get a closed form solution for W. However, that does not stop us, because what we already know one way to solve for this, right? So if we cannot compute a direct value for W by setting the derivative to 0, we can do something which we have seen before, which is gradient descent. We can compute the gradient of LL, right? That we can do. So if you go home, you can actually work this out, right? You can compute D of LL of W given DW, and then you can sort of try to do the gradient descent procedure and try to get the best W. So if you actually work this out, the gradient looks like this. The gradient of the log likelihood with respect to W has this form, where theta I is essentially 1 over 1, it's a sigmoid of W transpose Xi. So you can compute that, right? And then you can do the gradient descent rule, all right? So which means that you start with some W. So this is a sort of a figurative illustration. So let's say you have only 2 elements in your W, right? So you start, and the third dimension tells you the log likelihood. So you want to reach here, right? But what you do is you start somewhere, and that at every point you update your W in the direction of your gradient, and hopefully if your log likelihood looks like this is perfectly convex, then you will reach the top, right? But in reality, it might not look like that. You might have all kinds of ridges and valleys, then you would have issues. But in the case of this formula over here, this is a very nice formula, which means that this has this convex shape, which means you will reach the global maximum, all right? So in your programming assignment 3, you would be asked to do this. So remember this when you do 1 week from now. All right. So any questions so far? Yes.
We have to use the sigma system. I thought it was another question different.
I'm sorry. What was that again?
We have to use the same function in sigma here for the assignment.
This is for third assignment, so don't worry about it for the second one. What I'm saying is in the third assignment, you will be asked to write a gradient descent algorithm, right? Okay. All right. So I want to just mention one more thing. This is more general to optimization rather than logistic regression. Is that, remember, we have done stochastic gradient descent, right? So gradient descent. You have done that for assignment number 1. You are also going to do it for linear ridge regression in assignment number 2. However, in each one of them, we have to specify some eta, right? Which tells you how much do you want to move in each step, right? So in logistic regression you have, or in gradient descent, you have an update rule, and in that there is this scalar that you have to put in, which means that at every step how much do you want to move by, and sometimes that gets tricky to set, right? And we have talked about it earlier as well, that if you set eta to be very large, basically you're making very large jumps, so you might overshoot your optimal point. And if you make it very small, then you might take a long time to converge, right? So setting that is kind of like an art. There is no principled way. However, there is another method in which you do not really have to use an eta, okay? So in that, what you do is, actually that's a mistake here. There's no eta here. In this, what you do is you update in a very similar fashion. You go in the direction of your gradient, which is here, but you use something called the Hessian, which is the second order derivative of your log likelihood, and move in that direction, all right? And that helps you move in the right direction. So these are called second order optimization methods. So gradient descent is what we call a first order optimization, in which you're only computing the gradient, right? So remember, we say that your weight at time t, or iteration k, is going to be the previous weight plus eta times the gradient, right? The gradient is just the first order derivative, d by dw of your whatever function you have, right? Which is fine, but the issue is that setting eta is hard. So these are first order methods. The second order methods say that you can go by using which means that you still compute the gradient. So gradient is again the first order derivative, and the Hessian is actually the second order derivative, right? So you know how to do the second order derivatives, right? So what you do is you compute the second order derivative, multiply the inverse of that with your gradient, and you move. So if your function is j, right? Let's say j is of course a scalar, your error, right? So j belongs to r, then your gradient will belong to rd, which you have computed, right? That's the error gradient, because you want to compute the derivative with each element of your w. And the Hessian is actually a matrix, because you are computing, you will first compute the gradient, and then you will take the second derivative of the gradient with respect to your weights, right? So your gradient is a vector, your weight is a vector. So you will compute every pair derivative and you get a Hessian. So that's why here you see this inverse. So you compute this matrix, take an inverse, and compute that, and that will those methods, these second order methods, the benefit of those is that you do not have to rely on a single scalar eta to direct how much you want to jump by. It comes from the data itself, and they have been shown to have nicer properties. So they converge they converge faster, and they tend to be more accurate. All right?